All right, so chapter 8 is all about logarithms and logarithmic functions. Today we're going to focus on writing log expressions in exponential form and vice versa. So exponential in log form, and then we're going to analyze those different functions. Okay, so because you've already done this worksheet, you already have a working knowledge of some of the things we're going to talk about, which I think is going to be really helpful. One of the questions I get asked about a lot during this section is, what is a log, but what is it? So what a log does is it is a relationship between an exponent and the base. So it's the exponent to which a specified base is raised to obtain a given value. Okay, so a log is just evaluating that relationship between the base and the exponent. Okay, so you can write an exponential equation as a logarithmic equation. You can write an exponential equation.
Please, interruption at this time. Please release the bowlers. Please release the Hazen High School bowlers.
Okay, so you can write an exponential equation as a logarithmic equation and vice versa. So if you had a log, you could rewrite it in exponential form. So the relationship between them is if you have log base b of y equal to x, okay, this is interchangeable with rewriting it in exponential form, which would be b to the x equals y. Okay, for example, if you had log base 2 of 8 is equal to 3, and when we're writing these, I just like to be intentional about the way we're writing. So I don't know if you guys remember one of our favorite elementary school activities. We have this paper, right? So when you're writing this, okay, the log goes here. This base is a subscript, okay? The base is 2. It is of 8. And that is equal to 3. So this needs to be lower. And we can't have this floating. The log, the 8, and the 3 should all be on the same line. All right? And then once you have that written out, you can write this in exponential form. The exponential form should also be true. So your base, one thing I give students to help them remember is just remember bay. Not before anyone else, but base, answer, exponent. So the base is 2, the exponent is 3, the answer is 8. Okay, so this is your exponential form. Okay, so your base, your answer, your exponent. Okay, and then of course if you try to write it in a different way, it wouldn't be true. Like you couldn't write 2 to the 8th equal 3. 2 to the 8th is not 3. Okay? All right, now some of you have already found the button on your calculator that is a log. That is what we call the common log. So if you are using that button, it is actually a log with base 10. So log base 10 of x is the same thing as just saying log of x. So if you have log base 10 of x, you'll commonly just see it like this. Okay, so log with base 10 is the log button on your calculator. We will be looking at that today as well. Okay, the log with base 10 is the log on your calculator. All right, so for example 1, it says write each exponential equation in a log form. So it's given an exponential, you have to write it as a log. Okay, so again, just make sure you're writing this correctly. You want your log, and then your base is a little subscript here. So it's log base 3 of 243 is equal to 5. These should all be on the same line there. Okay, for B, you actually have two different ways you can write this. So this is log base 10 of 1 equals 0. But because this is the common log, you can just write it as the log of 1 equals 0. Okay, anytime you have base 10, you have the common log. All right, so based on those, I want you guys to do C, D, and E. Okay, so again, there's two ways that you can write this one because base 10 is the common log. You can just write the log of 10,000 is equal to 4. If you wrote log base 10 of 10,000, that is okay too. That's still correct. Okay, for this one, you have log, your base is 6 of 1, 6, and that's equal to -1. Okay, and then the last one is a log, base A of C is equal to B. Okay, so when you take the log is analyzing what the exponent should be for the given base and this value. Okay, so 3 to the 5th is 243. 10 to the 0 is 1. All right, and then in example 2, now we're going to go the other way. So we're given the log equation. What we're going to do is write it in exponential form. And this is when you can use your base answer exponent. Okay, so this is your base, this is your answer, this is what your exponent should be. Okay, and then exponential form was just 9 to the 1st equals 9. Okay, so I'll give you less than a minute to do the rest of them. All right, so then we have 2 to the 9th equals 512. 8 squared is 64. 4 to the -2 equals 1/16. And b to the 0 equals 1. Okay, so these are a little easier for us to check because we know the way exponents work, so we can see those are all true statements. There are certain patterns that emerge whenever you have logs. So we're going to talk about those special properties. The first one is when you have a log of base b and you're taking the log of b. Okay, so we're just using b as any value. So if you have the log base b of b, that's going to equal, we can look up here, if you have log base 9 of 9, what is that equal to? 1. So this is always going to happen. Okay, whenever you're taking the log of a value with the base of that same value, okay, it is going to result in 1 because the value raised to the first power is going to be the same value. Okay, so if you were to see log base 2 of 2, then you would know, oh, if they have the same base and the same value there, that has to equal 1 because 2 to the first equals 2. Okay, and then the second special property is the log of 1. So it doesn't matter what your base is. Okay, if the log is of 1, that has to equal 0 because of our special rule that says anything to the 0 power is equal to 1. Okay, so this is actually the exact same as your part E there. Okay, so if you have log base 4 of 1, doesn't matter what the base is, this is always going to equal 0 if the log is of 1, because anything to the 0 power is going to be equal to 1. Okay, so now we're going to take all of this knowledge and we're going to use this to help us evaluate. So the directions will say evaluate using mental math, so without your calculator. And so your work for this section is going to be to write out your exponential form, just like we did on our practice sheet today. Okay, so when you're evaluating using your mental math, you're just going to write each log in exponential form as your work. Okay? All right, so for A, we have log base 5 of 125. For B, we have log base 2 of 16. And C, we have the log of 0.01. We're going to start with those three. Okay, now what's different of these is they're not equal to anything. All right, that's what we are going to evaluate. So you can think of this as equal to x, yep. And now we can set up our equation, okay, our exponential equation. So your work would be 5 to the x equals 125. Okay, and then from there you can solve just like we did on our worksheet. So what would your x value be? Yep. So your answer for A is going to be 3. All right, so for B, you're just going to do 2 to what power is 16? 2 to what power is 16? 4. Okay, so you can just put that it equals 4. That's perfectly fine. Okay, now for C, we can't see what the base is, which means the base has to be what? 10. Great. So this is going to be 10 to some power equals 0.01. Now there's two ways that you can think about this. Because we're using mental math, not a calculator, I like to rewrite it as a fraction because the 1 is in what place? The hundredth. So this is the same thing as 1 over 100. And this is something that we've been working on, right? So 10 to what power would be 1 over 100? -2. So then I would know my answer for this is -2. Another way you can think of it is in terms of scientific notation. So in scientific notation, you could move the decimal over to get a 1. Do you guys remember with scientific notation, it has to be between a number between 1 and 10 times 10. So that's why you do it to 1 and not 10. So if you move it 1, 2 places, this is going to be -2. Okay, so you can use either one of those for part D, which is the log of 0.00001. So it's 0 and then there are 4 zeros and then a 1. so I want you to write that out and try that. Okay, so I've seen people with both of these, so no matter which one you are using, okay, you're going to have to pick what your pattern is. Like with the 10 to 100, see how you had 2 zeros and you had 2? You could count your zeros here and you could do that. I used the decimal in this case since it was a larger decimal, and I just counted 1, 2, 3, 4, 5 places. So if it's 5 places, your value for x is going to be -5. All right, and then for E, your base is 25, so 25 to what power is 0.04? So again, I might rewrite that as a fraction. So it's in the hundreds place. What is 4 over 100 reduced to? 1/25th. And then from there, right, from 25 to 1 over 25, we know that's just going to be what? -1. Okay, so you have 5x to the 1/5. In this case, x is going to be -1. Anytime it's the same number, but it's over 1, you're going to have -1 as your power. All right, and then let's try log base 4 of 1/64. Okay, so 4 to what power is 64? 3, so this will be -3. Great. All right, now we are going to graph log functions, and we are going to use our graphing calculator for this. I'm going to show you some tricks on there. And then we're also going to talk about the relationship between log functions and exponential functions. So log functions and exponential functions, they are inverses of each other. So they are inverses, which means their graphs are reflections of each other over a special line. Okay, their graphs are reflections of each other over the line. Do you guys remember what the equation is? We did this like before we took our first semester exam, right? There is that special line of reflection. Do you guys remember what that was? Yep. So over the line, y is equal to x. Okay, and then remember, when you find the inverses, those x and y values are going to switch. And that means the x values, because they're tied to the domain, and the y values, because they're tied to the range, those are going to switch too. Another thing that's going to switch is the asymptote. So remember for exponential functions, we'd always have y equals. It was a horizontal asymptote. Now for log functions, it's going to be a vertical asymptote, which that means you're going to have a vertical line and it's going to be x equals a value. Okay, many times it will be x equals 0. And And then when you're graphing, you just need a table with at least 5 values. You can put more on there. And I'm going to show you how to pick out some good values in your table. And then we're also going to be using graph paper for those. So we're going to graph the function, find the intercepts, domain, range, and end behavior. So you might remember that our domain for all exponential functions was all real numbers, but the domain and range are going to flip for inverses. So now our range is going to be all real numbers. So the range for log functions is all real numbers. We're also going to show that's true with the graph. Okay, and then I am going to let you use your graphing calculator to do this. There are ways to do it without just choosing separate values, but I think it's important for us to analyze what happens here. So we're going to go to our y equals. Some of you have a log-based function, so I'm going to show you how to do that first. You're going to click the math button, and then if you arrow down to its choice A, it says a log base on it. Okay, so you can choose the log base, and it will let you put in any base you want. So you can choose the 1/4 and the x. Okay, if you scroll to your math and you don't have that option, that's okay. You're going to use the change of base formula, which is something else we're going to talk about in this chapter. It just comes in a later section. Another way that you can write this as the log of x divided by the log of 1/4. Okay, and depending on the year of your calculator, you might have to plug it in like this. I'm going to plug in both so you can see it's going to be the exact same thing. So it's the log of x divided by the log of 1/4. Okay, and then what I want you to do is explore your table. So on your table, is there anything special about that? Is there anything that you notice about the table? Yeah, there's errors in the table. Where do those happen? Yeah, so the negatives and at 0. That's because when you are doing a log, you cannot take the log of 0 or negatives. Okay, you cannot take the log of 0 or negatives. And if you think about it, that makes sense, because if you plug in a negative as an exponent, remember, it doesn't make it negative, it makes it a smaller fraction. Okay, so you aren't going to be able to go past a certain point with your x's. Okay, so what we're going to do is we're going to start plugging in some values. On the table, I like to make a note here, like for -1 and 0, that you do get an error, so you know that that's okay. Okay, because you can't take the log of those, that's okay. All right, and then let's find some nice values here. So at 1, I'm at 0. Okay, yeah, whenever you have the log of 1, it's 0. We talked about that earlier today. At 2, you have -1/2, so that's a nice value. And then you have a decimal. At 4, you have -1. Let's see if I can find another nice number. At 8, I have -1.5. Find the next nice one. The next nice number. Yeah, 16. 16 is -2. And then look at these values here. See how you have the 2, 4, 8, 16? Okay, these can all be rewritten with a base of 1/4, which is why those end up being like nicer numbers. Okay, you can see it's being multiplied by 2. Okay, so it makes sense that you have that. Like I said, I'm letting you use your calculator, but this is really what your calculator is doing. Your calculator is doing the log of 1/4 of 16, okay, and telling you that that equals -2. 1/4 to the -2 is 16. Okay, so you're answering 1/4 to what power is 16 there. Okay, now when you are looking at your graph, so you might have to go back to Zoom Standard to get to your standard window, depending on what you last graphed. Okay, this graph is lying to you a little bit because this keeps going forever, okay? But because of your calculator's limitations, they can't make it that small to have it keep going. But those numbers are getting really, really small as they're getting closer and closer to the asymptote. Okay, the asymptote here is going to be at x equals 0. And that stems from this here. Okay, so x equals 0 is your vertical asymptote, and we are going to put that on our graph. Okay, we also have to remember that we're going to extend this out. So on the video, you aren't going to be able to see this because I'm putting it on the smartboard, but I want you guys to see. This is the line. Oh, no. Okay, this is the line that you're going to be graphing is this. Okay, so this whole line here. Okay, so you got to put the arrows on both ends, and then we're going to be putting the asymptote at x equals 0. Okay, so that's what we're going to be graphing on our paper. Okay, so even though your calculator stops there, it's just that limit in technology. Okay, so let's put in our asymptote, and then let's think about what a good scale is going to be here, because I need to get to 16. So on my x's, I'm probably going to want to go by 2's. So 2, 4, 6, 8, 10, 12, 14, 16. And then based on my y's, I'm going by a half, so I should do that. So I should go by halves. All right, so at 1, 0, 1 is halfway in between. At 2, I'm at negative 1/2. At 4, I'm at negative 1. At 8, I'm at negative 1.5. And at 16, I'm at negative 2. If you ever wanted to see what happened in between there, you can change your table set. If you want to see what happens at like 1/2, okay, you can see that that's at 0.5, so it would be above here, so it is going to keep going, okay? I just want you to see what I'm telling you about it. Keep going, it's the truth. It doesn't just stop here, okay? It's going to follow this line, and you're going to put your arrow on both sides. Okay, so you're going to put your arrow on both sides there. Okay, you can also see that all of the values for x are at 0 and above, which means your domain is going to be x such that x is greater than 0. Okay, and then it said to find the intercepts. So the x-intercept is on our chart. It's 1, 0. It's on our table. The y-intercept, in this case, there are no y-intercepts because that's where your asymptote is. Okay, so we found the intercepts. We did the domain and range. The last thing we have to do is the end behavior. So the end behavior for this is a little bit different. Okay, so I want you guys to set up our standard end behavior sentence. So as x goes somewhere, f of x goes somewhere, and as x goes somewhere, f of x goes somewhere. Okay, so we always want to talk about what's happening on the right side and the left side of the graph. Normally, the left side of the graph is negative infinity, but that's a problem here because this side of the graph is not going to negative infinity. It's getting closer and closer to what? 0. So this is as x goes to 0, the end is approaching. So where's the end going? To infinity. Great. Now this end is going to infinity. And then as the x is going to positive infinity, the y is going to negative infinity. Okay, great. I have graph paper for you.